This is Ben Goertzel, and I'm going to summarize for you now some of the ideas in my AGI-20 paper, What Kind of Programming Language Best Suits Integrative AGI. And I mean, this title of the paper I framed in a quite general way, and I am interested in the general question, but this is a topic that is also acutely practical for me now because I'm engaged together with a bunch of my colleagues in SingularityNet and the OpenCog project, engaged in looking at a fundamental redesign and substantial rewrite of the OpenCog AGI engine that we've been working with a long time in the course of our research on artificial general intelligence. I mean, we've been tongue-in-cheek calling the new system we're building OpenCog 2.0, founded on the Atom Space 2.0 new weighted labeled hypergraph. Of course, that's a bit of a tongue-in-cheek name because the current OpenCog and Atom Space are not really at what you think of as a 1.0 version. I mean, we're still, in some senses, at the early stage of the OpenCog AGI research project, although we're also aware that at some points in a research project, the early stage can accelerate quite rapidly to the later stage. And of course, we're hoping to cause this sort of acceleration with the fundamental, re-architecture and rethinking that we're doing in the OpenCog 2.0 and Atomies 2.0 project. So redesigning the whole OpenCog system is a large undertaking. In this talk, I'm going to focus on a few particular aspects of it. I mean, this diagram here shows it at a very high level, how we're thinking about the overall system that we're building. I mean, you have a distributed atom space, which is a distributed weighted labeled hypergraph or a generalized hypergraph representation. You can do a bunch of learning and reasoning on this atom space. Usually that will be done on locally cached subsets of the atom space. So you can do reasoning with logic engines, automated program learning, neural networks, whatever algorithms you want. You can also embed the nodes and links in this atom space into a vector space and use neural net or other machine learning libraries on it, and you can extract symbolic patterns using pattern mining from the atom space. And there's attention allocation processes that determine which aspects of this distributed atom space or its local cache will rise to the attention of any particular algorithm at any point in time. So this overall architecture and approach to AGI has been described in depth in the book Engineering General Intelligence that was by myself and my colleagues Neil Geisweiler and Cassio Penashim. We've had a lot of advances since that book was written, but the overall conceptual framework and high-level architecture that was outlined there is still the one that we're proceeding with now. But the deeper you get into actually doing something, the more weird little difficult problems you see deep in the weeds. And here in this talk, I'm going to get a little bit deep into the weeds of what we call the Atomese language in the OpenCog world, which is really an example of a programming language being developed with AGI in mind. And one of the complexities of the Atomese language is the fact that there's an aspect where it's intended as the internal representation language of an AGI system, and there's another aspect where it's something that humans are supposed to be able to read and write, and getting these two requirements to cooperate nicely together can be challenging because, of course, a lot of what happens inside the mind of an AGI system is too big, complicated, and screwed up for human beings to look at. Now, you can have more or less syntactically sugared versions and more or less efficiently, rewritten versions within the same language, and then automatic program transformations between different representations of the same semantic content in the same language, and that's fine. But then your language has to define how that works. And in the current OpenCog version, basically we have a vocabulary of nodes and links in the Atom Space weighted labeled hypergraph knowledge store. These nodes and links can have types and complex relations between them. And then working with OpenCog in practice, some of it's about setting up these nodes and links, and some of it's about writing code to manipulate nodes and links in an external scripting language, usually Scheme. You can also use Python or Haskell or C++, which is the base language the current OpenCog system is written in. And it's a bit awkward going back and forth between essentially programmatic structures within the Atom Space and programmatic structures in some scripting language that's used to manipulate the atoms in the Atom Space. We want to get rid of that barrier and make an Atomese language that is how the Atom Space represents stuff, but it's also something you can practically use to write scripts for defining cognitive processes that use the Atom Space. And in order to have the same Atomese language for both of these purposes, I mean, you need to have a fairly sophisticated approach to managing types and doing program transformations between different versions of the same program in that language. So just to ground this a little bit, just to show one code snippet before jumping into high-level sort of design principles, abstractions, and ideas. So here's a bind link written in Scheme, which is the way we often represent these things working with OpenCog, which basically recognizes a little pattern for recognizing jaywalking in a street scene based on the output of deep neural net models that are applied to various cameras looking at the street scene. So this isn't an especially important bit of Atomese. It's just to show you the kind of thing we're looking at. There's a bunch of different types of nodes and links, including concept nodes and variable nodes. There's links with semantics like member link, apply link, inheritance link, which has logical semantics and a probabilistic truth value. There's a typed variable link and a type node that says a certain variable node has a certain type. So this is not just dots and lines. These are nodes and links that are with a complex semantics embodying various logical, programmatic, neural, and so forth constructions. And here we see the use of Scheme to manipulate these links, which has worked for quite some time, but it's awkward. And we want to come up with one Atomese 2.0 language that does what Scheme is doing here and also does what the system of nodes and links are doing here, but does a better job than either Scheme or the current Atom Space node and link system. So in designing the whole OpenCog 2.0, Atomese 2.0 system, there's a whole bunch of questions that we address or need to address. I'm going to run through these key questions here. We're not going to try to answer all these key questions in the few minutes of this presentation. And the paper that I'm summarizing here really focuses on the first three questions here. What core formal language do we want for our weighted labeled hypergraph formal language? How do you interpret or compile this language? If you need to use specialized languages like sub-languages, how do you go between the default Atomese languages and the sub-languages? And then what does this language look like from the point of view of a human reader or programmer? I'm not really going to get into that too much. Then these next issues, we're not especially going to go into in this talk. They're not touching the paper, but they're things that I've thought about a lot and will be posting some writings on publicly before long. So I mean, how do you architect the local cache of the Atom Space? You can call the weighted labeled hypergraph or a generalized hypergraph, because in Adams space you can have links pointing to links, which you don't have in a hypergraph is usually considered. My colleague Anton Kolonin likes the term metagraph, which is like it's a hypergraph that can have links pointing to links or links pointing to whole subgraphs. So the current OpenCog Adams space code is sort of suitable as a RAM-based local store, like local cache of a huger distributed Adams space. And the huger distributed Adams space we don't really have in the current OpenCog system. I mean, we have a Postgres backing store that can store an Adams space to be accessed by a bunch of different local Adams spaces, but we need a much bigger, more scalable and more flexibly manipulable and queryable distributed Adams space hypergraph. Then, what libraries do you need? What libraries are critical to support particular AI algorithms and approaches, logical inference, automated program learning, and so forth? How do we integrate Adamese programs with external knowledge stores and libraries? So if you look at Alexei Potapov's paper from a previous AGI conference, he introduced something called cognitive modules, which explained how you can interface neural models and neural model learning in Torch with OpenCog Adams space in a relatively sophisticated way, where a Torch computation graph is passed along between different atoms in the Adams space, and the computation graphs corresponding to computations corresponding to two different Adams space nodes could be composed if those two nodes are composed. So the correspondence with external libraries like a Torch or TensorFlow can actually be quite subtle, and that's a requirement for Adamese language, that it can be used for effectively interoperating with some of these external libraries in an efficient way. So what are some key ideas that I think can be used to solve the first three problems on the previous slide? I'm going to run through a few of the key ideas we're looking at in the Adamese 2.0 design, which are mostly ideas I think are of significant general relevance to the problem of creating programming languages for AGI, even beyond the setting of OpenCog and Adams space. And I would add these ideas while I'm presenting them here in my own way. I mean, these have come out of discussion with a bunch of others, including Alexei Potapov, Nil Geisweiler, Cassio Penashin, Linus Vepsas, Vitaly Bogdanov, and a whole bunch of other members of the OpenCog and SingularityNet community. So a key idea is the third one on this list. I mean, the pattern matching process that we have in OpenCog now is sort of too big. I mean, pattern matching in OpenCog, it can try to match a static pattern against a hypergraph and find everything in the hypergraph that matches that static pattern. It also does some dynamic pattern matching, which is cool, meaning it can sort of rewrite or transform parts of the hypergraph a little bit until they match the pattern. And that's interesting, but it's become quite complex. And we want to move in Adamese 2.0 to a simpler pattern matching process where you have a simple static operation like match this pattern at this locus, at this particular place in the hypergraph, and then move the locus of pattern matching along this link or along this traversal. So you need to break down the pattern matching process into atomic operations and expose these atomic operations explicitly in the Adamese language. And this isn't done in current Adamese. It's not really done in a general or explicit enough way in other pattern matching centric languages like Haskell either. And we need to do this in a way that works well with distributed and concurrent programming, and that does well with timed pattern matching of temporal patterns, which are really important in real-time learning. And if you need pattern matching to be efficient, if you need it to be especially efficient, for a certain set of of predicates or schema that's of interest, a certain set of nodes, I mean, then how do you make it easy for a developer to make this pattern matching efficient? So these are some of the key issues. And making pattern matching in general work in a way that's easily customizable to make efficient sub-pattern matchers for particular types of nodes and like this is really hard. And some of the other things I'm going to talk about in the next few minutes are just as hard or harder. And I think the only thing that makes some of these things perhaps, presumably solvable in the near term is that we don't have to solve them in absolute generality. So one of the peculiarities of the use of an Adamese type language for AGI is it's all about the knowledge store, really. Deep neural net methods, which are quite popular today, are mostly about matrix multiplication in various forms. But the OpenCog style of AGI, which I think is exemplary for integrative multi-algorithm, multi-paradigm AGI. Here we have the atom space as the sort of central whiteboard that multiple AGI algorithms are acting on. But the same point I'm going to make would hold if it was some other sort of representation that was a central blackboard or whiteboard on which multiple AGI algorithms were cooperating. The key issue here is that most of the work computationally is looking stuff up in this vast multi-algorithm knowledge store or putting stuff into the knowledge store. Most of the work is not doing like number crunching or some isolated symbol manipulation algorithm independently of this atom space knowledge graph. Of course, in OpenCog, you could write a cognitive agent that just solved differential equations or factored large numbers rather than spending its time writing from atom space. But using OpenCog for that would be kind of pointless. So we're assuming that most of the processing time for Adamese programs is taken, looking for patterns, which may be unforeseeable dynamically generated patterns, looking for patterns in particular locales of the atom space, or applying some rewrite rules to small portions of the atom space. And the fact that most processing time is assumed to be taken up with these things is why some of the hard computer science and programming language design and implementation questions we're confronting may be solvable in this case that we're looking at, when they might be harder to solve if you were trying to solve them in a language that was good for everything. So you couldn't make, we're not trying to make an Adamese language that would be efficient for, say, an arbitrary modern C++ program, like writing the operating system for a laptop. But in the same way, C++, which is good for writing the OS for a laptop, isn't necessarily effective for integrative AGI purposes. And so a couple of the peculiarities we come up against here, which would be very hard to deal with in a totally general purpose context. We need to do pattern matching, not just about static data. We need to do pattern matching against variables. You can have variables pointing to variables, pointing to variables, pointing to variables. And you need to match individual query terms against whole graphs. And none of these things work in Neo4j or standard graph databases. And making them work in total generality with efficiency would be hard. But I think for the cases we care about for AGI, it may be a solvable problem. And so we, to do this, we need flexible ways to manipulate atoms, and including atoms that include rewriting rules for mapping, like rewriting a whole subhypergraph into a subhypergraph. We also need flexible ways to define type system and specialized indexes. And an index, say a spatial index, a temporal index, an episodic memory index, whatever it is, an index or a type system need to be first-class citizens. They need to be defined within the same metagraph, the same generalized weight-labeled hypergraph that the atoms themselves live in. And I mean, then if you define a type system in the atom space metagraph, you should be able to plug in a type checker and a type inference system here. So one of the conclusions we've come to is, we probably need fairly sophisticated type systems here. I mean, you definitely need higher order types, and you need dependent types where the type of this can depend on the type of that using type variables. See, I mean, the programming language AGDA, AGDA, is a better guide than Haskell, which is a better guide than imperative language or than Scheme or Lisp. But we probably aren't going to be able to define like one type system to rule them all for every part of a vast distributed AGI mind. I mean, the type system that works best for probabilistic learning in a highly uncertain environment may be a certain kind of like second order probabilistic type system, whereas the type system that you want for certain types of program learning, you may not care so much about probabilities or higher orders. So you want to be able to have different parts of a vast globally distributed atom space operate according to different type systems. And you also want to have some knowledge that can span the different type systems in the different parts of the atom space. So that leads you to a gradual typing framework. Like some atoms have types defined in specific type systems. Some atoms have incompletely specified or non-specified types. And this is quite interesting in a theory context. If you look at Curry-Howard isomorphisms, it's, I think, like gradual typing on the programming language side sort of morphically maps into a pair-consistent logic on the logic side, and OpenCog's PLN logic is a certain kind of uncertain pair-consistent logic. So I think we already have sort of logical tools for reasoning about this kind of gradual typing working in OpenCog. But how do you make something this abstract be efficient, right? And it's clear we care about probabilistic types. We care about linear logic, which takes the kind of resources, as well as dependent types. We may need various methods, such as isotypes, as one example, to make type checking more efficient when we get to this sort of abstract sort of type system. But making gradual typing with these fancy abstract type systems reasonably efficient is an insanely hard problem in functional programming language design, except we're dealing with a case where almost all your processing time is taken looking up stuff in the atom space and doing local rewrites on the atom space. So that, I mean, what that means is it doesn't matter too much if you're type checking and like type inheritance inference is sort of slow. So yeah, we're digging here kind of into the guts of type systems, gradual typing, pattern matching, and so forth, which are, these are issues that are coming up in our work trying to create an Atomies 2.0 language. They're the type of issues that are familiar to anyone who's gone deep into functional programming language design in any context. And I think they're going to be relevant to anyone that's trying to create a sort of native language for an integrative AGI system, meaning an AGI system that wants to put together AIs operating according to multiple algorithms derived from multiple paradigms, cooperating on a very large common knowledge store. And, we've gone a bit further with these explorations since I wrote this paper, but I will defer that to a later presentation. So I'll leave you with this now, except to note that, we're actively seeking knowledgeable, creative, energetic collaborators in our attempt to, massively upgrade and rewrite to OpenCog AI system and create the Atomies 2.0 language. We're doing this open source. We're going to roll it out on the SingularityNet decentralized AI platform among perhaps other channels, and we're interested in using this to solve applied problems in genomics, biology, natural language processing, IoT, all sorts of other applications, as well as using this to work toward general intelligence. Clearly, there's going to be multiple different routes that could get you to AGI, but I think the direction that we're playing with in OpenCog, of which these musings about programming languages are a critical part, albeit more the infrastructural than the cognitive level. I think this is one highly viable path, and it's a path I think has the highest odds of rapidly getting us to beneficial AGI. Thanks.